people. Okay, so, You guys are familiar with the home page. Today we are doing the M&M lab. Then your homework is to do a pre-lab question quiz. That's these questions, only they're online. And to do the electron energy and light packet, what you just picked up. If you look in there, you're going to see a stop sign. Multiple stop signs, actually. Do not stop at the stop sign. You are doing the entire packet. Okay? It'll ask you to color. Use color. I like color. Okay? Helps stick things out. Okay, so anyway, those are the things you need to do today. If you look at the Flame Lab questions, they are your pre-lab questions plus a few more to make sure you actually read the lab. Okay? So read the lab, do the pre-lab questions, submit, bam, done. Any questions about your homework? Okay, excellent. All right, so were you guys okay with drawing a wave?
Yeah.
Yeah? It's very simple. Waves are just upwards and downwards fluid motion. The amplitude is the height of the wave. The crest is the top of the wave, and the trough is the bottom of the wave. A node is when the wave equals 0. It comes to an equal point. This little guy right here is called lambda, okay? That symbol of the upside down Y, his name is lambda, and he stands for wavelength. This guy right here is nu, NU, and he's a very fancy V, and he stands for frequency. Let's see. Oh, next, what are the units for wavelength? That's important. How do you measure a length? What? Yeah, excellent. So a wavelength is from one point to the same point. So a crest to a crest, a trough to a trough. And wavelength is measured in meters. Okay? So radio waves are really big and they're measured in meters. And then light waves are really small. They're measured in nanometers. All right, what about frequency? What's the units for frequency? Hertz. That's the abbreviation for hertz, Hz. And hertz can also be written as 1/seconds. It can also be written as seconds to the -1. So frequency has 3 different units that you can use. They all work. You just have to recognize which ones are which. All right? All right. Okay. So as you have a wave and it's going up and down and up and down and up and down, if I increase the frequency, or how many times I go up and down, up and down, up and down, what happens to my wavelength? Braxton. What happens to my wavelength? Oh, looks like we got to do some calling. Okay. If I increase my frequency, what happens to the wavelength? Down. Very good. Excellent. For those of you at home, we just discovered that relationship. All right, next one. If I increase the frequency, what happens to the energy? Up. And what about the wavelength and energy? Beautiful. Okay. We talked about this last time. Inversely and directly proportional. If both of them go the same way, that's called directly proportional, right? And if one goes the opposite way, that would be inversely. We all caught up? Almost. Keep going. All right, so that's what we covered in class last time. Any questions on the top part? All right. Let us move to the 3 equations that you're supposed to know. Da, 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 da. First off, what was one equation? Give it to me. You read it out of the book. Perfect. C equals wavelength times frequency. That is also known as C equals lambda nu. Good. And what does C stand for? Speed of light. Speed of light, which is excellent because Leo is wearing his astronomy mask. It's true. And what is the speed of light? Perfect. 3.00 times 10 to the 8th meters per second. So yes, that is almost 3 giga. Anyway, a giga is 9, right? And that's 8. So that's a whole lot of space in not a little, or in a little bit of time. Fastest thing we know of. Good. What's the next one? Is it the photon or the quantum? Both. It's all E's. Well, the energy photon is perfect. Energy is equal to Planck's constant times nu. Okay? So E is for energy. I don't know if you guys didn't know that, but just in case you didn't, it is. H is Planck's constant. And it is 6.626 times 10 to the negative 34th. Oh, shoot. I forgot the units. Can somebody help me? And the units are? It's joules seconds. Thank you. Joules seconds. Beautiful. Okay. So is that negative 34? Yes, that is negative 34. All right. For these equations, do you have to memorize them? No. Take out your periodic table. They are right here. These two up here, those are those equations, and the speed of light and Planck's constant are right here. Okay, so you don't have to memorize these. You just have to know how to use them. Okay? Now, there is a third equation that you have to come up with or use a little bit of math to get. So looking at this, yes? Try it.
Frequency equals to energy divided by wavelength.
Okay, you're actually really close. But, nice try. All right, so this is how you do it. Here's some math for you. Which variable does 1 and 2 have in common? They both have frequency, right? So what I'm going to do is I'm going to take this equation, number 1, and I'm going to solve for frequency. How do you do that? How do I get frequency by itself? Yeah, I got to move it to the other side. So I'm going to divide by wavelength. So frequency is equal to C divided by wavelength. Everybody okay with that so far? Now that I have frequency, if I look over here to my second equation, can I take C over lambda and plug it into here? So frequency, this and this are the same thing, right? Both are frequency, and frequency is equal to C over lambda. So can I take C over lambda and just put it in its place? Yeah, I can. That's what math does. Good. So what I'm going to do is I'm going to write energy is equal to H, and then I have C over lambda. Have I done anything wrong? Yeah, all I've done is just solve for one variable and then place that variable in another equation. So then my final answer, my final equation is energy is H times C divided by lambda. Do we need to go over any part of that math again? Okay, excellent. So this is what I would like to do. Over on the side, for each equation, there are two variables that are being related. So for instance, in number 1, this equation relates lambda and nu, wavelength and frequency. What two variables are related in number 2? Energy and frequency. All right, now somebody else, for number 3, what are the two variables in number 3? So for number 3, for equation number 3, what are the variables? Wavelength and energy. Because H and C are constants, so they're not variables. We know them. So these are the two that are related. You doing okay back there, Colin? Yeah. Okay. All right. This becomes important because if I ever need to calculate how much energy there is and they only gave me the wavelength, I want to know what my equations are and what relates. Okay? All right. How's that? Good to move on? All right, here we go. Example problems. I'm going to try to get that so it's in there. Okay. Orange light has a frequency of 4.8 times 10 to the 4th seconds inverse. First off, whenever you read a question that's relating these, you have to figure out what that thing is. So it tells me that the frequency is this. So I'm going to write that out over here. Frequency is 4.8 times 10 to the 4th inverse seconds. Then it says, what is the energy of 1 quantum of light? Anybody remember what a quantum is?
Equation?
No, it's a definition actually. Beautiful. A quantum is the minimum amount of energy. It's like the smallest amount of energy that can be transferred. So I want to know what is one small measurement of energy. What is the energy of orange light? So that's my question. Now, looking at my equations, which are kind of obscured, but that's okay. Which equation relates energy to frequency? Yes? Good. This one right here, right? Excellent. Oh, sorry. Can you not? Do I need to move something? Or just. I know, it's amazing. Okay. So, what we do is, first thing you do, you identify the information they give you. You identify the variable you want, and then you find the equation that relates those two variables. So then all I have to do is energy is equal to H nu. What is H again? It's a constant. It's this number always, every single time. Okay, and I've got to erase this so I have some room. And then I'm going to multiply it by the frequency. Okay, one thing they like to do with these kind of questions is they like to mess with the units. So always check your units before you put it in your calculator. If I take joule seconds and multiply it by seconds inverse, what's going to cancel out? Good. These seconds cancel out, right? And I'm left with joules. Is joules the unit for energy? Yes. Energy's units are joules. Okay? So that means that I did it right and everything's going to work right. Then I take out my calculator and I plug it in. Go. Everybody take out your calculator and plug it in. Now that I have my answer, 3.18 times 10 to the negative 29th joules. Now I just need to do sig figs, right? That's the thing you do after every problem. So how many significant figures did I start with? 2. So my final answer will be 3.2 times 10 to the negative 29th joules. Excellent. Okay. Moving on. The next one, I saw a lot of you guys do. Here we go. I have a wavelength, which is lambda, and I want to know the energy, which is E. So which equation am I going to use? Yes, yes. Very good, the third one. Energy is equal to Hc over lambda. All right, so first thing, identify what you have and what you want. Second thing, find the correct equation. Third thing, plug it in. Energy is equal to H, which is 6.626 times 10 to the negative 34th joule seconds times the speed of light, which is always 3 times 10 to the 8th meters per second, all over the wavelength, 193.3 nanometers. Questions on that? Nope? Good. Before I plug it into my calculator, I am going to check to make sure all of my units will match. So, will seconds cancel out with 1 over seconds? Yes. Seconds are on bottom here, and they're on top here, so they cancel out. Will meters cancel with nanometers? No, they won't. So before I can do any calculations, I need to change this guy into meters. How do you do that? Bless you. Well, we learned a very simple way, dimensional analysis. Nanometers to meters. 1 meter is 10 to the 9th nanometers. Right? So I get 1.933 times 10 to the 1, 2, negative 11. Or there's another way you can do it. Since this doesn't want a final answer, what you can do is just get rid of that nano and put a 10 to the 9th like that. And that saves you a step. 1. Do you see how that works? So either way will work. It doesn't matter what you do. You can either convert it and get here, Or you can just put in the 10 to the ninth where the nano is. All right. So now if I look at it, my meters cancel out, correct? Meters on top, meters on bottom cancel out. I'm left with joules, which is my unit of energy. And I type that into my calculator, and do you get 1.03 times 10 to the negative 18th joules? All right, so for this one, the answer is 1.028 times 10 to the negative 18th joules. All right. And I made a mistake before. I said this guy turns into 1.933 times 10 to the negative 11th. It's actually 1.933 times 10 to the negative 7th meters.
What?
Oh, do you remember when I did the dimensional analysis? I did it in my head and I accidentally got the exponent wrong. I know, it's awful. All right, so let's move on. You guys are going to have questions like that, and that's basically what we deal with whenever we're talking about light. And light is what we're going to focus on, especially next time with our flame lab. So try out these questions and be comfortable with them. All right, next one, electromagnetic spectrum. You guys looked that up in the book, and you got something like this. Something like that. Okay, well, let's just talk about it. So, the visible spectrum is the part that we can see. Can we see very much of the electromagnetic spectrum? No, not very much at all. Okay, so what we can see is actually not a whole lot of what's going on around us. It would be really rad if we could. Oh, am I recording? Yes, I am. Okay, so you guys have heard of infrared. That's what they use to see into buildings. And you've heard of UV, like UV lights coming from the sun, all right? So, if I were to look at this chart that you wrote down, who has more energy? Gamma rays or radio waves? How did you know that? Good, good. And this increases by frequency. Frequency and energy are directly related, right? Beautiful. Okay. Any questions on the electromagnetic spectrum? The only thing that you guys will have to have memorized is the visible spectrum. So, anybody know how you memorize the visible spectrum, or the trick there is to memorizing it? There you go! See? It's a good thing you joined our class. We would really... There you go. So red, then orange, then yellow, then green, then blue, then violet. So how I memorize it, or how most people memorize it, is Roy G. Biv. And then you can memorize what order they're in. And as long as you know that violet has the highest energy and red has the lowest energy, then you can just figure out in between. Okay? So a question might be, who has more energy? Green light or orange light?
Green.
Green. Very good, because green is closer to violet. All right, excellent. Next one on your notes is Heisenberg's uncertainty principle. What is that? Anybody look that one up? I told someone to Google it. Yes, go for it, Juan.
Probably uncertainty of measuring particles.
Yes, and in simpler terms, when you look at an electron, you can't know where it is and how fast it is moving at the same time. You cannot. Yes, rewind to where? Okay, uncertainty principle. Heisenberg found out that electrons, you can know where they are, and you can know how fast they're moving, but you can't know that at the same time. So you can't know where an electron is and how fast an electron is moving at the same time. So if you think about it, think about a ball. And when you throw a ball, you know where it is, right? And then when you throw a ball, it's moving very fast, right? And so you don't know exactly where it is. But with a ball, it's moving slow enough that you can see it move. With an electron, it's moving so fast, you can't see where it is. Okay? Yeah. So it's like a really, really fast baseball or something like that. Okay. All right, next one. Anybody want to describe diffraction or light wave for me? Okay, question. Is light a particle or a wave? It's both. So if you look at light, when you put light in here and you had these two splits, do you see how it makes those ripples?
Yeah.
That's just like water, right? You can see that it's a wave. However, light's also a particle because if I shoot light at something, in this case, I'm shooting it at a negative filled backdrop, the light will actually hit an electron and pop it off. So light is both a particle and a wave. And on your notes, this is how we know it. We used a diffraction grating to see that it looks like a wave. And we used the photoelectric effect to find out that light is like a particle. All right, excellent. So those are the notes. Any questions about those guys? All right, so tonight what you're going to do, that packet I gave you, the electron, the light one, that's going to walk you through how an electron works, and that will get you prepared for our lab tomorrow. Yes. When I said tomorrow, I mean the next time I see you. Yes. Okay. All right, excellent. Have any further questions on the notes, just let me know, and I will see you guys later.